So I'd like to talk about NVMe array. Actually, I had the similar engineering session last year as well. It's kind of honor to give you some updates and progress of our program. So through all the export we've seen yesterday, it seems like NVMe SSD was introduced as Lightning by Facebook a couple of years ago. And after that, some other vendors were developing this same type of PCIe NVMe-based SSD, the JBuff. But this year, the only change we observed is that they changed the form factor from the SSD point of view to make it more denser. So like a ruler or M.2 or M.3 type of things based JBuff. But we are taking a little bit different approach to make a more smarter JBuff based on NVMe SSDs. So we'll talk about NVMe SSD-based the JBuff that can provide a better efficiency in the data center. And then we'll talk about some applications that can be used, targeted with this product. So before we begin, we actually demonstrated our product last year, which is a prototype version though, but T20. That was one new chassis size and then 20 drives in it. And with the new generation of NVMe JBuff, we call it NV array. NV array will have 2U24 as upgraded to 2U24, and it will include HA capability and software enablement and capacity increase. So we'll go a little bit deep dive on those items one by one. So I'll talk about demands first for this type of storage. So we saw many of increasing demands or emerging demands that require high bandwidth and low latency. So UHD, for example, that requires double bandwidth than full HD resolution. So we have internal kind of customer who worked on the content delivery networks, and they require upgrade their infrastructure significantly. But if they want to have the right solution to meet their requirement, they need more than tens of copies of hard disk to provide the same level of bandwidth. That increases complexity of the management of the hardware too. So that really likes the product to provide the right bandwidth using quite simple configuration. So UHD is the one application we like to target, and virtual and augmented reality also requires large amount of data bandwidth, capacity, the latency, low latency type of things, because that VR or AR stuff requires even beyond like a 4K resolution to provide a real feeling, right? And 5G, as telco company, so 5G is one of our kind of emerging demand that requires a higher bandwidth at low latencies. And we'll talk about that later. But we saw the 5G is just upgrading the radio speed or latency that requires significant change, a dramatic change on these infrastructures as well. But from the 4G era, they rely on the dedicated infrastructures or ASIC type of thing. But as they move to 5G, they need to realize x86-based system and software. They need to define some functions by software. So as they move to 5G, connectivity are tremendously increase, and that requires x86-based system. So 5G era will change most of part from the infrastructure point of view. And composable infrastructures are another key feature that we need to target, we need to support for emerging applications as well. So dynamic configuration is also required for efficiency in the upcoming infrastructures. So storage with the large capacity and low latency, high bandwidth, and composability are key component for recently required infrastructures. So this is our NV array at a glance. We have two pieces of our product, but mainly our hardware is focused on like the NVRA E24, which is described on the right-hand side. But it requires some connectivity. So IHBA need to be put in the server side. So up to 10 server can be connected to NVRA at the same time. So dual port NVMe SSD will be required to provide HA capability. So that's the difference between the last generation and this generation. And base management controller with the Radfish and IPMI are also new, the feature of this product. And 10 upstream ports are required, the support. That means they can connect to 10 servers, host servers. And HBA is also have 8x8 option, by 16 option to provide the right bandwidth. So NVRA can be used as desk pool. So the NVMe JBUF been introduced so far, that supports only kind of the storage in JBUF only. That doesn't mean any sharing capability. So for example, Lightning, once you connect the server with the Lightning, that can give you more capacity, a little bit of bandwidth increase, but that doesn't give you any other efficiency, something like data sharing, something like that. But we'll enable some data sharing capability by our software to provide a better efficiency. That means that it doesn't have any redundant copy except the data protection purpose. So they can minimize the copy, which means they can save costs by using the NVMe SSD. So using the conventional, normal software, they can just use some amount of SSD to assign to the specific certain server. But by using our software, that could be released to open source. That could be by leveraging our software, they can be all the data can be shared among the software, host servers too. So I'd like to talk about some features and progress here. So NVRA, how we can share, how we can provide a sharing capability to host using our software. So we are leveraging NTB functions of PCIe fabric chips. So using NTB window functions of PCI fabric chip, we can provide the sharing, the window, and the data window the other servers can see. So through NTB functionality, we can provide a data sharing capability. And we evaluated some path like this. The server can share, they need to communicate the command level first, but data doesn't have to come to the real owner. That just goes to the requested the host directly. So that gives the maximum bandwidth to the host. The NVRA structure is described here, that we leverage GFS2, which is distributed system as well, to provide a sharing capability. But not just only GFS2, SKT NVRA software will be required as well. And beside that kind of capability, we like to enable multipath type of thing to increase the performance and increase reliability. So we like to talk about that. So the NVRA device driver, we call NDD, are positioned between block device and NVMe driver now. But next generation, we like to put that into the NVMe or PCI fabrics layer and then open source it. So I like to compare where they are using the pictures of our software layer here. So our target to make our NVRA driver to be placed in line with the NVMe of RDMA, NVMe of TCP or FCC, something like that. So layer 5, we like to put our software in the layer 5. That's our target. But currently, our software is in between block driver and NVMe driver now. And reliability, we actually were surprised that the PCI hot plugging is not quite ready in the industry, although it's been introduced 5 years ago, I think. So we are still keep up with the latest change in the industry, but it requires some amount of components be supported to support real hot plug stuff. So I'd like to share our experience here. So to support reliable hot plug on the PCIe side, that requires system BIOS. The proper system BIOS setting we required. Without system BIOS, which is like all generation server, using all generation server, that doesn't support any the hot plugging the capability type of thing. So that's one of the reasons that we need to use the latest server. And also Linux kernel, we need to use the latest Linux kernel as well, because only the latest Linux kernel has DPC, which is downstream port containment driver. That supports PCIe hot plugging capability, but that's still evolving now. So we are currently using 4.15 kernel version, but we are expecting 4.16 with the DPC updates. So DPC is on one of the key components to support hot plug, PCI hot plug properly. And kernel also need to be configured to support the hot plug in a proper way. So PCI hot plugging is not just easy, but it creates a dependency between hardware, BIOS, and kernel version. So I'd like you guys keep in mind if you are interested in PCI hot plugging stuff. Performance. I'd like to talk about multipath. Well, as we move to E24, multipath and dual port drive has been newly used. So before this generation, we just rely on single port NVMe drives. We haven't seen this type of things, problem. But as we start to move to HA capable hardware and then enable multipath driver, we found some issues. The first issue was like a performance. Although multipath was enabled, only one path been used, and then the other path used until unused until the used path failed. So we are changing now. We improved actually the driver to use multipath at the same time to increase the performance. That's not been submitted yet because we are running some tests using this, but we implemented this at the basic level, and then we saw some performance increase and the improvement. So basically, although dual port NVMe is used, multipath driver is not ready from the standard. So only half of the performance been observed by users. So current driver is supporting using only one active path, which is by 2 NVMe SSD, but another by 2 is unused, and that's just used as standby. But we enabled the active driver, so we can utilize by 4 fully using dual port. The performance increase like this. From the read perspective, since all those performance bound to the PCI lane, so since we increase number of lanes, the performance increased significantly. But the write performance is relatively bound to the NAND. So the performance increase is not that high as the read though, but this is the chart that we can show. So this is based on Samsung drive actually. But when we test the other vendor drive, that showed a little bit lower improvement by using active multipath driver. That means although we enable multipath driver, we improve multipath driver to use active path, there is some dependency on internal SAS architecture. So by enabling multipath active the driver, I think a driver vendor SSD vendor need to consider the more optimized architecture internally. And this is the kind of experience we've contributed in the mainstream. So we have repaired actually multipath driver as well. So when we multipath enable, the order between head namespace and hidden namespace been reversed. So with the original driver, although head namespace is not in place, the hidden namespace been created. So that caused some kernel panic and some incomplete actions. So we changed the order to have head namespace created first and the hidden namespace created later. So by changing the order, we address those kernel panic type of issues. So this is our experience we've contributed in the industry, and this is the kind of commit link we've done. So you can refer to this. And composability. This is kind of one of the emerging key feature that, required to the new hardware and then the solutions. So since the composability is required in the new industry, so we try to provide that type of capability from the BMC level. So we are leveraging the Radfish capable BMC. And by using Radfish capable, supportable the BMC, we can provide the composable NVMe storage pool as well. So not just only data sharing capability or HA stuff, but also like composability from the NVMe storage above are supported too. All right, target application and the test results. So as I said, like high res, like 4K, even beyond 4K, the resolution is requiring double and triple bandwidth from the storage. And then to meet the requirement using the current existing solution, it's going to be very hard, or that at least requires multiple copies to provide the double bandwidth or triple bandwidth that's required in the market. So I put the capacity, that also requires capacity. So not just only bandwidth that requires like terabyte, 100 terabyte, the capacity to provide the right contents to the end users. So that's the one target, and the virtual desktop infrastructures. Currently, for virtual desktop infrastructures, that concerns about some data dedupe the ratio. So using the sharing capability, data dedupe ratio can be achieved as they want. So that's one of the key, the target application of ours. So that requires bandwidth and latency too. I'm sorry. Oops. And real-time data analysis, that's one of the applications, and the AI deep learning infrastructures. Internally, SK Telecom is developing AI infrastructures too. So they're requiring large bandwidth and large capacity, the storage system. And 5G infrastructures, as I said, like that requires x86 basis infrastructures and some composability and low latency, high bandwidth. So that requires our storage as well. And I'd like to compare the NVMe JBOF versus NVMe over Fabrics. So NVMe JBOF is kind of previous or predecessor of NVMe Fabrics. But NVMe Fabrics is not just free. That's not simple. That requires additional CPU resource, additional switch, storage switch. But for the JBOF, that doesn't require any additional switch. That can just hooked up with the servers directly. But the limitation of that, the storage is the number of servers that can be connected to the storage. So for a mid-scale, like as SSD scales so fast, we can leverage that kind of trend. So using large capacity SSD, we can provide 100 terabyte of storage by just 2U JBOF. But if it requires like petabyte scale storage, definitely that will need NVMe Fabrics. So I think NVMe Fabrics is not a cheaper solution. But that requires, that will be required in certain area and certain requirement. But we can choose either one based on the demand and then the requirement. All right, I'll give you some case we've done so far. That's one of the key progress that we have. We had real tests using 32 client servers to generate tens of users, real users, that generate 320 gigabps workload generation. And then we application software running on the off-the-shelf servers, and then very connected to the servers. And then they can provide a full bandwidth required 320 gigabps. So actually the NVRA can support up to 400 gigabps, but they require only 320 gigabps though. So we tested based on their requirement. But we did the same test using all-flash NAS, but that showed only 50 gigabps. So our internal customer actually disappointed about the performance of all-flash NAS, but they're happy with the NVRA, which is quite simple. And VDI application, that's another target of ours. So we tested Bootstorm and some file copy tests, but all the VDI infrastructures wasn't actually CPU bound before, but as fast storage comes in, and then some bottleneck and the limitation of CPU capability being shown. So that's another finding of ours. So once CPU bottleneck's gone, then we provide a much higher the productivity from VDI stuff. Yeah. Future work, we'll keep sharing our experience, and then we plan to share our spec and all the design of OCP later. Summary, significant challenge in supporting new applications using just existing solutions. So that requires kind of upgrade of the storage system. Not only effective capacity and reliability, but low latency, composability are key factors for the new storage. And all-flash storage is being redefined around NVMe. So all-flash array has been replaced. All-flash array replaced the hard disk-based storage, just leveraging the SSD. But as the NVMe SS comes in, we need to redefine all storage stack and the storage parts. So to utilize NVMe, the protocol and the efficiency. All right, so we have another session. That's actually done, but you can check the YouTube or any other proceedings for our telemetry stuff. That's about the composability and the telemetry stuff for not only storage and servers. That's pretty much for our talk. I just have 20 seconds. Is there any question?
A quick question while we set up the next speaker if someone has a quick question. Okay. Otherwise, in 2 minutes, we'll be up again.
Thank you.